careful here.
Dr. Annan?
Yeah.
Sorry, can you repeat what mod it was in, the negative 43?
Oh, it's in mod 72. It's this mod over here. So the solution that you come up with is unique modulo 72, which is the LCM of 8 and 18. Okay. All right, so that's what you do if the mods aren't relatively prime, and you can't make them relatively prime by any trick that you know of. If you had, you might be wondering, well, what if you had 3 of them that were like 3 equations that were like that, right? Well, you'd have to do the process again, right? You'd have to do the first 2, get a single congruence, which would now be x congruent to negative 43 mod 72, and then tag that one along with the 3rd equation and repeat the process again. I'm not going to do that to you, but that's what you would do. That'd be like not fun. So, but that's how you would do it. Okay. Okay, so that was that. Okay, that was only part A. Got a few more parts here. Let's try this one. Find all solutions, if any, to, here's part B. X to the 4th plus 5x cubed plus 4x squared minus 4x minus 3 congruent to 0 modulo 52. Any thoughts here? Okay, how does 52 factor? 2 squared times 13, right? Okay, so we could look at it mod 13, and we could look at it mod 4. The idea here would be then that you could try and solve it mod 13, try to solve it mod 4, and then do what with the 2 solutions? Try to remainder and everything, right? So again, when the mod is not prime, right, when the mod is prime, you usually do things like Fermat's little theorem and so on and so forth. But if the mods are not prime, like here, factoring the mod into its different prime powers and working with the equation in each of those prime powers is a great idea. Okay, so which one do you want to do first? Mod 4 or mod 13? 4, gee, I wonder why. 4 is so small, you only have 3 possible x's that really have even a shot of working, right? Which are, well, 4 possible x's, 0, 1, 2, or 3. In mod 4, everything is either 0, 1, 2, or 3. So let's look at it. Let's try and, I always like replacing harder problems with easier problems, and this is definitely an easier problem. In mod 4, I definitely think, even in a test setting, I could probably try everything and see if anything works, right? What else is good about mod 4 in this case that kind of, is attractive to do with this? Yeah, it just reduces, right? I mean, you don't have to, why do we need to have a 5 floating around when we can reduce it? So how does this reduce to? Go ahead, Anthony. Minus 3, I'm going to write it as plus 1, but that's fine. Okay, so a very, very simple equation here, right? We're trying to solve this one. Okay. Now what? Let's just try everything. So try everything. Try 0, try 1, try 2, and try 3. Anything work? I didn't think so. They don't work. So 0 doesn't work, 1 doesn't work, 2 doesn't work, negative 1 doesn't work. No solutions. What it's really saying, guys, is that this polynomial here is not even divisible by 4, let alone being divisible by 52. If you can't solve it mod 4, you're not going to solve it mod 52. This is a kind of a trick, if you have a large mod to work with, and something is supposed to be true modulo a large mod, it also has to be true modulo any divisor of that mod. which means you can shrink the mod down to something small where you can just brute force it. You can just test every single case. So the answer to B is there's no solutions. Okay. All right, let's try a part C.
So if you tried doing a mod 13, you'd be wasting a lot of time. If you tried.
Yeah, that's why when I asked the question, do you want to start with mod 4 or mod 13, I was really glad when you all said mod 4. Because mod 13 wouldn't have been as, well, I mean, I could see, especially with plenty of time, you could test 13 numbers here. But you wouldn't be able to reduce, you wouldn't be able to cancel any of the terms, right? You wouldn't be able to get something so simple here. So it would be doable, but, you know, I'm not interested in, you know, having you guys do problems where it's just like an endless mind-numbing calculator process. So you shouldn't be expecting there to be problems where that's the idea. Right? That's not what I want. That's not what I'm going to want to ask you about. That's not what I'm going to want to ask. Okay. Okay. I have one more part here to this. So part C. So again, find all solutions if any. Here's the problem. Negative 2x squared plus 5x plus 1 quantity squared congruent to 0 mod 29. Okay. If I have just a real quick reminder about something from early on. If I have that P divides a product of two numbers, A times B, and P is prime, what can we conclude from that?
P divides A or P divides.
Right, P divides A or P divides B. This is really important to remember, and it's only true for primes. It's not true for composite numbers, but for prime numbers that is true. So is there any reason why that's relevant here?
You don't need to square.
This squaring business is totally unnecessary because if 29 divides the square of the number, then it has to divide the number. Right, so you may as well focus your efforts here on this thing right here, this quadratic compound. Okay, so that's the idea. Okay, so now this may or may not happen. So we now have a prime modulus. And it's a quadratic equation, so there's at most, so we're trying to find all solutions. What's the most number of solutions we could have? Just two, right? That's the Legendre's theorem. In a prime modulus, that's certainly the case. So there's at most two, but there might not be any, right? There might not be any. We have to go through the process. Do you guys know how to do this? Kind of from about roughly a month ago. Go ahead. We could use indices, that would work, but that would mean I'd have to go to the hassle of finding a primitive root here, and then I'd have to like work this all out. It would be doable, but I want to go with another idea maybe. Derek?
Change a variable?
Change the variables. And do you know how we do that? Remember this?
2ax plus.
Okay, so there's a change of variables, and the change is y. So I'm just doing this to remind you of the formulas. Okay, what was the equation for y here?
2ax.
Great, 2ax plus b. All of this is mod p, in this case mod 29. Okay, and then can somebody remind me what d is? D squared is easy to remember because it's part of the quadratic formula that you learn in high school. So it's just b squared minus 4ac. So we can work out what d is pretty quickly right away. And by the way, the a, b, and c, of course, are just these numbers here. A, b, and c. Okay, so what is b squared minus 4ac? 25 plus 8, which is 33. I don't think that sounds familiar. Probably because I did this late at night or something. Oh, I might have reduced it. Is that what it is?
Yeah, it's 4 mod 29.
Yeah, so it's just 4. Okay, good, that's right. Oh, well, that's easy. So then y squared is congruent to 4 mod 29, okay. Alright. Okay, so y squared is congruent to 4 mod 29. I'm pretty sure we can all solve that for the 2 and only 2 solutions that we can have, which are plus and minus 2. Okay, and now it's just a simple process to go back and figure out what x was. So I'll just maybe do the first one. So 2 would be congruent to 2ax plus b, so that would be negative 4x plus 5 if I did it right.
Also mod 29?
And this is mod 29. And so if I want to get x, that's just 4x is congruent to 3 mod 29. I guess I need an inverse for,
You need.
I need an inverse for 4, don't I? What's an inverse for 4? Yeah, negative 7, right? Because 4 times 7 is 28. So I really want negative 28, so I'll multiply by negative 7. So that gives me negative 21, which is perfectly fine, or I can add 29 to that, and I would get 8 in mod 29. So one of my solutions is x congruent to 8. Okay. And then I just use negative 2 to get the other one. Maybe I'll just tell you what the answer is. You guys can try it later. So the other one, for y equals negative 2, you're going to get x congruent to 9. So you guys can check that because it's the same process. And I'd rather move on to bigger and better things. Okay. Okay with that? Yeah, go ahead. It would just be right here. This and this. You just put them both down.
Remember this one where you keep adding and you'll put dot, dot, dot? Like you keep adding them on.
Oh, well, you mean so I'd change 9 to 38 or something?
Yeah, and
And
you
then-
put comma and dot, dot, dot.
If I'm asking you to list, let's say I ask you to list the 5 smallest positive solutions or something, then you might want to just start making a little list and just grab the first few. But there's never really a case when you have to do it that way. This is really representing all of the solutions pretty well. Yeah. Okay. Let's. We're getting through this. I've got something else I didn't talk about though. I wanted to do. Okay. Let's try a couple of these. This is very recent material. What number am I on?
We're on 6 now.
This is number 6. Okay, beautiful. Number 6, find a representation for n, capital N, as a sum of 2 squares, if possible. Alright, so the first one, we're going to have a few of these to practice on. The first one is just 500. Okay. So it's not too bad, but what do you usually want to do with the problem? I know we didn't have any homework on this, but it's simple enough. I think we can all handle the process with this. So what is the first step? Exactly, you want to prime factorize this number. I pretty much just think of this as 5 times 100, and I already know that 100 is 2 squared times 5 squared, so I'm just getting one extra factor of 5 in there, so it's just 2 squared times 5 cubed. Okay. Now what?
Separate the square free.
Right, you want to re-express, so now you've got the prime factorization, you want to re-express it as a perfect square times some leftover factors, right? So how would that look in this case?
100 times 5.
Yeah, the 2 and the 5 can both be squared, that's 100 really. And then the one that's left over on the outside is the 5. Based on that, so this was the notation that we had in our recent theorem at the end of the semester about this, so we write it as n squared times m. Based on that form, do you guys think that this one is possible or is not possible?
sorry, the ends are different, right? When you say find a representation
Oh,
for n.
jeez. Oh, yeah. Can I just make a quick change here?
Little n? Okay. I was confused.
That would be better. That's a good point. Thank you for clarifying that. We'll use a little n for that. Okay, so do we know the answer to this? Yeah, the theorem is very simple, guys. What the theorem says is that when you look at the square free part, just make sure that there are no primes of the form 4k plus 3. Right? So you put all of the possible primes that you can inside this perfect square part. The stuff that lingers outside at the end, as long as it's of the 4k plus 1 form, you're good. Okay, so the answer is yes. Now the one thing that you do have to still do, it says find a representation. To do that, you're going to need to take this square free, each of these primes that are here, in this case there's only one, and figure out how to write it as a sum of two squares.
Well, 5 is 1 square.
So this is such a simple small number. The one thing that could catch you up is if there was a huge number of the form 4k plus 1, a huge prime number of the form 4k plus 1. We don't have an algorithm for how to write that kind of a number as a sum of two squares. Okay, so don't worry about, don't look in the book for theorems about that. We don't have one. But as long as the numbers are pretty small, it's not very hard to figure it out. So this one is just 2 squared plus 1 squared. So we have basically 10 squared times 2 squared plus 1 squared, and then the trick from there is to just multiply it through. Multiply the 10 squared through, and you get your formula. Okay? That's pretty easy. And if there are more than one leftover primes out here that you're looking at that are all of the form 4k plus 1, then you might have multiple sums of squares for each one. But then remember, we have the lemma. You guys remember the lemma here? We did it just very recently for how to. So if m is a squared plus b squared and n is c squared plus d squared, it might not be a bad idea to learn this formula because you may need to use it to re-express, right? Remember this? That's how you take a product of two things that are already sums of squares and make them into one. Look familiar? Okay, great. Let's try just a couple more of these just to really make sure we're all good on this. So part B. Part B, I chose n equal to 6, 7, 8, 9. Oh, I was going to give you the factorization. Sorry. Well, there is clearly, if you add up the digits, there's a factor of 3 in there because they adds up to 30. The digits add up to 30, so you know it's going to be divisible by 3. But then even after that, you get 2,263. So I'm going to give you this. It says 3 times 31 times 73. So it's actually the entire thing is square free. There's no perfect square at all in that thing. Okay, and so then the question is this representable as a sum of squares? And if so, how?
No.
It's not, right? Because you have primes. I mean, this one's okay. 73 is fine. But 31 and 3 are both congruent to 3 mod 4, which means you can't express them as sums of squares. So we just stop right there. Can't do it. Okay, and then I have one more. And so just so we're all clear on this, just want to make sure. I'm really using, just a second, Jeff, I'm using theorem, this is theorem 13.3. And then there's a corollary, and a corollary on the next page. Basically, what it is saying is a positive integer is representable as a sum of two squares if and only if each of its primes of the 4k plus 3 type occur to an even power. That's basically it. Yeah.
If you didn't give us a factorization, since we can see that 3,263 is not divisible by 3, then we already have a 4k plus 3 that's going to be an odd, or it's going to occur an odd amount of times, and we just stop say that.
Like if there's no more 3 in it.
So you notice that, right, so you notice that, this is not divisible by three. And that it is of the form 4k plus 3. So it's a number that, okay, so,
I'm just saying, we have a 3, which is of the form 4k plus 3, so we can stop right there.
oh, I see what you mean. Yeah, so you could stop here and say, oh, I don't even know how this factors, but it doesn't matter how it factors, as long as you know there's not another factor of 3 in it. Remember, at the end of the day, what do you care about? You care about the square-free factors. You already know that 3 is one of your square-free factors at this point. So without having the rest of the factorization, yeah, that's absolutely true. You would know that it's not possible to be of that form. Okay. I thought you were saying because this number over here has the form 4k plus 3, that then there has to be a 4k plus 3 factor inside of here. So,
That's
for
correct.
example, if this was, let's just say, I don't know what that is now. I'm just changing it to this number really quickly. So if whatever this isn't what I was going to do next, but let me just say something about this one. So if I have this one, of course, the 5 is fine now. And you're looking at this number. This number is may or may not be prime, we don't know, okay? But it has the form 4k plus 3. Even if it's clearly odd, so if I express it as a product of primes, it'll be a bunch of primes of the form 4k plus 1 and 4k plus 3 multiplied together. But there will have to be an odd number of them, if you think about those primes, there will have to be an odd number of them of the 4k plus 3 variety. Now just think about multiplying these kinds of numbers together. So actually, so in mod 4, so 2263 in mod 4 is congruent to -1, right? So imagine, getting a bunch of, so here's a bunch of things in the form 4k plus 1. And now you're multiplying by, well, let's just start with some other letters here, L1 plus 3, or L2 plus 3, whatever, right? Some of these. So you decomposed 2263 in that form, right? As a product of some primes of the 4k plus 1 type, and some other primes of the 4k plus 3 type. Reduce the equation mod 4. On the left side, you get -1, right? On the right side, you get 1 times 1 times 1 times 1 times 1, and then -1 times -1 times -1 times -1 times -1, right? Which means you have to have an odd number of these to make a -1 come out on the other side of the equation. Well, that means that your 4k plus 3 primes cannot be all put into pairs and shoved into the capital N squared part. There's going to be a 4k plus 3 prime that ends up in this little m piece, right? And as soon as that happens, it's not expressible as a sum of squares, right? So that's another, actually, that was a point that came out of something Lisa said in class last week, because I proved this little lemma that if you have a prime of the form 4k plus 3, it's not possible to express it as a sum of 2 squares. But then we looked at the proof of it, and you made the comment, which is very good, which is that, well, the proof seems to work for any number. Any number that's of the form 4k plus 3 wouldn't be expressible as a sum of 2 squares. And now this is one way to see that. So you take a number like this, whether it's prime or not, I don't know, but you factorize it out. And if the number itself has the 4k plus 3 form, then there must be an odd number of prime factors within the number that also have the 4k plus 3 form.
So you can't look at the original number.
Yeah. So that's what I thought that's what I thought Jeff was trying to say at first. You just look at this and say, oh, that's congruent to 3 mod 4, therefore we're done. But yeah, you can just look at the original number in that sense. Right. Okay. I had one more I wanted to do. Are you guys feeling comfortable with this sums of squares thing? Okay. Maybe I don't need to do another one of those. Can I skip it? Got the idea? I don't think it's that helpful. That's fine.
It's a pretty big number, yeah.
Find something else. Find something else that may be more interesting. Okay, we're getting close to 6, so I don't want to be too long, but I'll throw a couple more things at you here. And come back over here again. I still have this this group work here. Jeez. Maybe I'll just pass it out.
You can just do
I
it.
thought I was gonna like be exhausted, but I'm like as energetic as I've been all day. I've been doing this since noon. It's amazing.
You used to do like this long review
Oh
sessions,
yeah,
right?
when I was a grad student at Berkeley, we would start about 6 or 7 o'clock in the evening, and nobody would leave until about 2 in the morning. Yeah, and everybody was like,
You're just reliving the old days.
it feels that way. Maybe I'm getting younger. Yeah, I don't know. Okay, what number am I on? 7?
Number 7.
Okay. Number 7, find all primes with exactly 4 primitive roots and find them all. Did that question make sense? Find all primes with exactly 4 primitive roots and find
All the primitive roots, all such primitive
Find
roots.
all 4 primitive roots. That's what I was trying to say. Sorry. Okay, that's what I was trying to say. All right. Find all primes with exactly 4 primitive roots, and then find all 4 of those
So on
primitive
your
roots.
sheet, you have choose one such prime.
Oh, we'll find them all.
Okay.
Well, this is before I thought about it. Okay. Actually, because isn't that true? Once you find one primitive root,
You can find them
we
all.
know how to find them all. So let's see if we can do it. First of all, we have to figure out which primes are they. It's amazing. There's only 2. There's only 2 primes for which this is true. Let's see if we can figure it out. We have to prove that we have them all. So what are we going to do?
BFP?
Yeah, the number of, we need to know how many primitive roots does a number have. So the number, so let's let P be prime. The number of primitive roots, we know that all primes have primitive roots. The number of primitive roots is phi of, in general it's just n, but because, n could be, it doesn't have to be a prime. It could be powers of primes or 2 times powers of primes, but it's that many, right? Which is, of course, what is phi of p equal to?
P minus 1.
Right, p minus 1. Okay, so we at least know that much. And so it's just, we would like to set this equation equal to 4, basically. And we want to know which primes have 4 primitive roots. Okay, any suggestions here?
Brute force.
What's brute force mean?
Try out a bunch of primes.
Oh, try a bunch of primes, but you're never going to be able to prove we found them all.
But once it gets to a certain point, once you get to a certain number, isn't it impossible for there to be 4 at some point? The numbers are going to get bigger and bigger and bigger.
I'd have to be convinced of that.
Okay.
That would have to be, I mean, that's basically going to be part of the proof that we're going to have to give. It's not, to me, that's not obvious. What would we do to start this out? You guys have done lots of problems that are like this before, where you've had phi of n, and it was set equal to a specific value. Here we're setting it equal specifically to 4. And we're just trying to solve for n. I don't think we want to get into the, necessarily get into the powers of